Hi there, and welcome to another module in the WANDA 2021 Nuclear Data Introductory sections. Today we're going to be talking about isotope production, and specifically the use of predictive codes for isotope production capabilities. So today what we're going to do is we're going to go through kind of a brief overview of how isotope production efforts currently are performed within the data community, and the role that these codes are currently used for, and what we can do with them. So let's go ahead and dive on in. So a little bit of background here. As we've heard quite a bit this week, nuclear data is central to a multitude of basic and applied science topics. These range all the way from more basic science applications, such as astrophysics, or the design of different accelerator components, to applied topics such as nuclear energy, criticality safety, non-proliferation. One area that sits on the boundary of these two is the area of isotope production. Now, isotope production, for those of you who might not be as familiar with the application area, is an interesting beast. The community focuses on the production of a variety of different radionuclides, which have a number of different applications, ranging from industrial tracers to medically valuable radionuclides used either for imaging or therapy. But one thing that really makes the isotope production community unique is that we typically want to produce isotopes that other communities don't necessarily care about. In general, our needs are motivated less by the isotope itself and how they might be produced or any sort of chemical or physical properties, but instead we focus really on the decay properties, the lifetime, any characteristic decay radiation, and other aspects associated with the decay phenomena of the isotopes themselves. So, how does isotope production actually work? As part of this module, we'll go through a quick overview, just in a nutshell, of a typical production pathway. The very first step in isotope production is to actually go ahead and produce the isotope itself, using a variety of accelerators, neutron sources. At the R&D scale, these irradiations might involve thin targets used for the collection of nuclear data. But once the production data is well characterized, these are going to look more like thicker, larger targets for the production of larger quantities, millicurie scale or to Curie scale, approximately, of the radionuclides in question. So after you've actually gone ahead and made the isotopes that are desired, the next step is to purify them, where we use a variety of radiochemical and physical means to separate out the radionuclide in question from the rest of the activated target material. The goal here being not only to remove and potentially, hopefully, recycle the original target material for further radiation and future production runs, but also, very importantly, to remove out any other radiocontaminants from the final product. From a medical perspective, this means the removal of other radionuclides that are chemically dissimilar from the intended radionuclide. However, because there are a limited number of separation techniques that can effectively separate out radionuclides at large scale, one of the main goals in the first step is to make sure that we are minimizing the co-production of other radioisotopes of our desired radionuclide, since these will become much more difficult to separate out at this stage. So at this point, for industrial tracers or other non-medical applications, the isotope would essentially be ready to go out for delivery following some quality control analysis. However, for medical applications, there is an additional step where we need to attach our radionuclide to a targeting molecule in a process called labeling so that we may deliver the radionuclide to its intended destination. A number of targeting molecules are routinely used, including antibodies, as these allow clinicians to be able to deliver the radionuclide to a specific site in the body or to a particular type of cell or the site of disease. The goal for the labeling process is to be able to design a targeting molecule that will selectively bring our radionuclide only where we want it to go in the body, thereby sparing the rest of healthy tissue and the rest of the body from any of the associated dose from our radionuclide. This step generally involves a large amount of research designing not only labeling molecules that can stably bind the radionuclide, but also to ensure that they can selectively deliver the radionuclide where we want it to go. And at this point, our labeled radionuclide would be ready to undergo the clinical trial process to get approval, or, following clinical approvals, clinical applications. One important thing to note about this pathway is that each of these steps is its own complete discipline on its own. And so without being able to combine together experts from each of these topics, the entire chain of isotope production would be an impossible task. But for the purposes of the talk today, we're going to be focusing mostly on this first step, just because this is the area in which predictive codes have the greatest application. One other particular challenge faced in isotope production is the fact that very often there are many potential production routes that can be used to produce the radionuclide in question. And so we've got a number of tools at our disposal to be able to work with this. In general, due to the radionuclides with a charge-to-mass ratio capable of being accessed through different channels, we tend to produce radionuclides on the proton-rich side of stability through the use of charge-particle reactions. Similarly, for anything on the neutron-rich side of stability, we tend to use high-energy or thermal neutron sources, just because these are the types of radionuclides that can be easily accessed with these sources. However, especially when a radionuclide in question is either tricky to make or there are a lack of good targetry options, one of the things that really makes the isotope production community interesting is that we really are scavengers. We will use anything it takes if it can produce a viable production pathway with high yield and high purity. And so we'll use anything at our disposal, anywhere ranging from neutrons to gammas to a wide variety of different charged particles. So let's give a brief overview of where isotope production efforts are currently performed. For charged particles, high-energy, high-current accelerators, such as the Lance-IPF and Blip-Linacs, and other high-energy cyclotrons, such as at Triumph or Itimba Labs, are routinely used as some of the workhorses for the production of longer-lived radionuclides. On the other hand, many lower-energy machines, such as the International Network of Medical Cyclotrons, university cyclotrons, and other lower-energy accelerators, can be more easily used for the production of short-lived radionuclides closer to the intended destination for production. In between, there exists a wide variety of other accelerators, both cyclotrons and linacs, that can be used for R&D of new and emerging radionuclides, as well as limited production, in order to facilitate preclinical studies and dose mapping studies with these developing radionuclides. There are a number of other ways in which charged particle accelerators can be utilized, such as the use of isotope harvesting or online isotope separation techniques at facilities such as FRIB or the Isolda facility. Overall, the charged particle ecosystem provides a wide number of different facilities spanning a range of beam energies, beam intensities, and available ion beams to be able to satisfy both the R&D aspect of isotope production, as well as to facilitate production in order to meet clinical and customer demand. But charged particles are not the only trick we have up our sleeves. Another common production paradigm is the use of neutrons, which can populate a very different set of radionuclides, which often are inaccessible with any useful sort of yield using charged particle-induced routes. And neutrons come in a variety of different flavors. Spallation neutron sources, which have a wide variety of neutron endpoint energies, can be used for symbiotic isotope production, as neutron targets can very easily piggyback onto other experiments which are currently ongoing in a spallation facility. A more common tool for neutron-based isotope production is the use of reactors, as they produce a massive flux of neutrons. In particular, Reactor production is well suited for radionuclides with long lifetimes, as the target material can be inserted into an irradiation facility and left to cook for extended periods of time. However, reactors are limited to either thermal spectra or fast fission spectra, which can potentially limit the number of reaction channels energetically accessible. For production routes which require higher energy neutrons, there are a number of ways to achieve a fast neutron source. One route which can take advantage of existing proton accelerators is the use of reactions such as lithium PN to produce a tunable and quasi-monoenergetic neutron source over a wide range of neutron energies. However, these routes do tend to be somewhat limited in their flux due to the thermal limits of lithium targetry. DD and DT generators allow for a fairly compact fast neutron source around 2.5 and 14 MeV, but similarly, these sources are somewhat limited due to the deuteron currents that can be practically run in such a generator without arcing or breakdown. In addition, there is very little control over the neutron energy spectra accessible in these facilities due to the kinematics of DD and DT fusion. Another potential neutron source, which can help address some of these issues, is the use of the deuteron breakup reaction on a variety of thick targets, which can produce a very broad energy, but also directionally focused and intense neutron source over a wide range of energies, though these do require an accelerator capable of running energetic and high-current deuteron beams. However, one common aspect for many neutron production routes is the fact that broad neutron spectra inherently produce a wide variety of different radionuclides, and as a result, these sources require a very thorough assay of not just the radionuclide of interest, but the entire network of isotopes that are produced, especially so for reactor production. As mentioned earlier, the isotope production community can be a very resourceful bunch, so there are a number of emerging options and production pathways currently under development. These range from the use of intense photonuclear sources for gamma-N or gamma-P production, which may be used for the production of radionuclides, which are inaccessible through the use of neutron or charged particle-based routes. Other emerging options are the use of tunable fast neutron sources, such as the use of deuteron breakup or lithium PN sources. And one common benefit that all of these have together is that with the growth for R&D in theranostics, which pairs an imaging radionuclide and a diagnostic radionuclide, either of the same element or of chemically similar elements together, for combined imaging and therapy, has expanded the list of radionuclides which the isotope production community considers interesting. With such an expansion, the isotope production community has started to reevaluate existing production pathways and existing targetry to start producing a wide variety of new emerging radionuclides for ongoing R&D demand. So now that we've had a very brief overview of some of the facilities and production routes used for isotope production, let's delve into the nuclear data side of things. Where does nuclear data come into this application field? Predominantly, this arises in the design of targets either for research irradiations or for production irradiations. The process of target development generally begins with a nuclear data measurement campaign. In such a campaign for a new production pathway, researchers will first seek to measure the excitation function for the production of a radionuclide. These campaigns will often make use of thin precision targets to be able to minimize the energy bin subtended by each foil. Charged particle-based production pathways will often make use of the stacked target technique or other similar approaches to measure the production cross-section at a wide variety of energies in a single irradiation. For neutron-based production routes, an excitation function may be obtained through multiple activations using neutron sources with a well-defined and narrow energy spectrum. Once production data have been obtained, they may be used to inform the design of a thicker production target for the production of large quantities of radionuclides. Such a design seeks to maximize the production rate of the radionuclide of interest, while minimizing the co-production of other radiocontaminants which may be difficult to separate out during the chemical processing stage of production. Thus, a typical data measurement campaign seeks to measure the production of all other competing reaction channels. However, even in this nuclear data renaissance, there is still a disturbing dearth of well-characterized reaction data across a broad range of channels. In the context of the nuclear data pipeline, which has been discussed in multiple previous WANDA sessions, nuclear data for isotope production tends to be predominantly focused within the measurement section, as these measurements tend to produce nuclear reaction data, including excitation functions, isomer branching ratios, decay data, and other associated nuclear data relevant to isotope production. However, even in this nuclear data renaissance, there is still a disturbing dearth of well-characterized reaction data across a wide number of reaction channels. In the publishing and compilation steps of the nuclear data pipeline, which is basically the body of existing experimental work, we can see that there are currently approximately 32,000 cross-section datasets available for all incident particle types in the X4 database. Of these, approximately 70% of these datasets are for neutron-induced NX reaction channels, often limited to the fission energy spectrum range or the DT 14 MeV spectrum, and often limited to target materials relevant to nuclear energy or security applications. Of the remainder, about a 20% subset of X4 datasets are for proton-induced reactions, only about 6,000 datasets. However, the need for further experimental campaigns relevant to isotope production becomes even more clear when we realize that of these 6,000 datasets, only about 18 guide our evaluation and modeling above 100 MeV, which is the important range of our regional LINACs that are commonly used for isotope production. Further, less than 3% of X4 datasets cover the use of deuterons and other heavier ions for isotope production. In terms of evaluation and recommended datasets across all energies, even from those 6,000 datasets for the PX reactions commonly used to produce a large fraction of commercial radionuclides, the range of data we have available is currently very limited, and there are especially very few evaluated heavier target cases, which are often the ones actually relevant to medical isotope production. So our basis of PX in terms of experiment, evaluation, and modeling work is generally quite sparse. We certainly don't know all that we should, and the situation for fast neutrons, heavy ions, photonuclear production, and other emerging production pathways is even worse. So, how does the isotope production community proceed when there's no data available, or the available data is of insufficient quality or breadth of energy? In these situations, modeling codes must be used to predict the excitation function in order to design thick targets or to guide the design of a thin target measurement campaign. However, as has been shown in a number of recent papers, modeling efforts using default parameters often fail to exhibit even modest predictive power. In cases where prior experimental data exist, this predictive power is often within a factor of approximately 20%, though the level of fidelity required is often greatly dependent upon the application field in question. However, for reaction channels which have not been previously measured, it is not uncommon to see discrepancies within factors of 2 to 3 or even greater. In general, several trends can be observed for the general state of modeling. Modeling is markedly improved for channels where data had been measured previously, as well as for strongly fed channels, and for reactions where ejectile particles do not need cross shell closures. However, a number of common underlying issues include the failure to model high-spin transfer reactions, failing to accurately model the shape of a reaction channel, such as an incorrect placement of the compound peak, or an incorrect calculation of the amplitude of the channel, as well as a difficulty with modeling the pre-equilibrium emission of ejectile particles. However, it is important to note that these trends are seen in cases where modeling codes are run head-to-head using default parameters. For these codes, users are able to adjust modeling parameters to be able to adjust calculations to reproduce experimental data, similar to the process used in the evaluation of reaction data. However, this approach can lead users into an easy pitfall, as the parameter space for optimization of reaction parameters is a massively complex landscape with a multitude of local minima. When making adjustments based purely on a single residual product channel, it is very straightforward to find a number of solutions which reproduce experimental data for a single channel to within an acceptable degree of accuracy. One example of this is seen for the production of niobium-90 through the pp3n reaction channel on 93 niobium. In this case, there are a number of parameter adjustments with varying degrees of success in reproducing this channel. In this case, models 1, 2, and 10 performing best over the default parameterization. Looking at just this channel, we can see that it's possible to make a number of different sets of adjustments that either reproduce or at least do better than the default parameterization. But of these adjustments of the reaction physics, which one represents reality best? Well, if we look just at this one channel, we can see that models 1, 2, and 10 perform best over the default calculations. Are we actually improving the predictive power from these codes? Have we generated some sort of information to help us improve modeling and get out a correct solution? These are questions that users should ask themselves as they make these type of adjustments. However, as soon as we look at a neighboring channel, in this case the production of molybdenum-90 through the competing P4N channel, we see that this approach is certainly naive, in that the models 1, 2, and 10, which previously performed well for the production of niobium-90, perform extremely poorly here. Users are cautioned to avoid this type of single-channel arbitrary parameter adjustments, which unfortunately are very common in literature and may clearly lead to compensating errors, as well as a non-unique local solution to the global reaction modeling picture. Clearly, to improve the predictive power of our reaction modeling codes, which will be the overall goal for this session of WANDA 2021, we need to develop a process for a more global fitting approach. This will be a topic of discussion for many of the lectures and presentations within this session. However, to provide some brief introduction to many of the concepts and many of the techniques and terms which will be described, we will now provide a brief general overview of nuclear reaction mechanics and the way in which a number of modern modeling codes use these mechanics for the calculation of reaction cross-sections. While px-based production pathways are commonly used for the production of a large fraction of commercial radionuclides, we will instead provide a more general overview of the basics of reaction modeling. Certain aspects of this will differ based on the type of incident particle used, but the majority of the formalities and concepts discussed here are common and underlying to the modeling of any reaction channel. To begin our discussion of the basics of nuclear reaction mechanics, let us first consider this figure, which exhibits some of the hallmark characteristics of nearly all of the reaction channels used in isotope production. Starting from the energetic threshold of the reaction channel, as we move to higher and higher incident particle energies, the reaction channel changes through several distinct energetic regimes. At lower energies, from threshold to approximately 10 to 15 MeV above threshold, the reaction channel is dominated through a compound reaction mechanism, observed as the so-called compound peak, seen here. These processes generally involve long reaction times, on the order of attoseconds, and are predominant at low energies. In contrast with direct reactions, which are mostly one-step processes, the compound reaction mechanism is known to proceed by many intranuclear collisions. In this mechanism, the incident particle is captured by the target nucleus to form a compound nucleus. Subsequently, the incident energy is shared among the other nucleons, and after a long time, a sufficient amount of energy may be accumulated for one nucleon, or a group of nucleons, to escape from the equilibrated nucleus. At higher energies, nuclear reactions are characterized by a direct reaction mechanism. These typically have short reaction times, on the order of zeptoseconds, comparable to the time it takes for the incident particle to traverse the target nucleus. These reactions also have a strong correlation between the initial and final channel of the reaction, as well as forward-peaked angular distributions in the outgoing particles, and a noticeable oscillatory resonance-like behavior. In general, the low-lying discrete states of the residual nucleus are almost completely excited by these direct reaction processes. Calculation of the direct reaction channel cross-sections are typically performed using either a distorted wave Born approximation or a coupled channels reaction modeling approach. These will not be the subject of much focus in this talk, as the energies for direct reactions are typically far above those used in isotope production, but the listener is encouraged to read more to satisfy their own curiosity. In between the compound and direct reaction mechanisms, as an intermediate between these two extremes, there exists a reaction type that embodies both direct and compound-like features. Such reactions are often referred to as pre-equilibrium or pre-compound, or, in a quantum mechanical context, a multi-step process. Pre-equilibrium emission takes place after the first stage of the reaction, but long before statistical equilibrium of the compound nucleus is attained. It is imagined that the incident particle, step by step, creates more complex states of the compound system, gradually losing its memory of its initial energy and direction. Pre-equilibrium processes provide a substantial portion of the reaction cross-section for incident energies between a few tens of MeV up to 100 to 200 MeV. The modeling of this component of the reaction cross-section may be further subdivided into a series of multi-step compound or multi-step direct reaction components. With these regimes in mind, let us now turn to how the total reaction cross-section can be subdivided into these individual components, that we may discuss the modeling of each of them more in detail. Typically, the total reaction cross-section may be divided into the elastic and non-elastic components. Typically, the nuclear optical model is used to calculate the elastic component of this total reaction cross-section, leaving behind the non-elastic component, which is comprised of the sum of both the inelastic scattering cross-section and the absorption cross-section. These tend to be dominated through compound mechanisms, and will be discussed in subsequent slides. At higher energies, the density of compound nuclear states becomes so large that the individual contributions can no longer be resolved. It then becomes impossible to distinguish the slow energy dependence of the elastic contribution from the rapid variations of the compound nucleus ones. Instead, only the average properties of the compound nucleus contribution to the cross-section can be determined. It is in this context that the optical potential plays a crucial role in the separation of these two contributions. The principal objective of the optical model is to describe the prompt elastic reactions in a nuclear collision. To separate the elastic reactions from the compound nuclear ones, one assumes that the compound nucleus reactions do not contribute to the average wave function and scattering amplitudes. This holds well for most spherical nuclei, but for statically deformed nuclei, a coupled channel calculation is needed for correction. The central assumption underlying the optical model is that the complicated interaction between an incident particle and a nucleus can be represented by a complex mean field potential, which divides the reaction flux into a component covering shape-elastic scattering and a component describing all competing non-elastic channels. Commonly, a semi-empirical optical model potential is used in modeling, comprised of a Coulomb term, a complex volume term, a complex surface term, and a complex spin-orbit coupling term. A number of parameterizations for the individual potential strengths of each term are available in the literature and employed in most modern reaction modeling codes. Solving the Schrödinger equation numerically with this complex potential yields a wealth of valuable information. First, it returns a prediction for the basic observables, namely the elastic angular distribution and polarization, the reaction and total cross-section, and, at low energies, the S and P wave strength functions, as well as the potential scattering radius. Additionally, not directly observable quantities that are provided by the optical model have an equally important impact on the evaluation of the various reaction channels. The most well-known examples of this are transmission coefficients for compound nucleus and multi-step compound decay, which may be calculated from the scattering S matrix. Additionally, the optical model provides distorted wave functions that are used for direct inelastic reactions, and for transitions to the continuum that describe statistical multi-step direct reactions. With the elastic contributions now removed from the total cross-section, we turn our attention towards the need for a model to describe the fraction of the total cross-section which populates various compound nuclear states. This is typically done through the statistical model, which derives from Bohr's independence hypothesis, stating that the compound nucleus cross-sections can be written as the product of a factor describing the creation of the compound nucleus and a factor describing its decay. The statistical model is a powerful tool to describe reaction cross-sections whenever a compound nucleus state is created. The major input parameter in the statistical model equations is this transmission coefficient. The main difficulty residing in the evaluation of the transmission coefficients is the need for a well-characterized nuclear level density, as this level density model is required to estimate the transmission coefficient for the formation of the compound nucleus. Within the statistical model, two main variants are employed for the calculation of these transmission coefficients. In Weisskopf viewing theory, only energy, charge, and mass conservation are accounted for. As a result, the transmission coefficients for the decay factor are proportional to the absorption cross-section summed over the projection of the particle spin. In Hauser-Feshbach theory, angular momentum and parity are also accounted for. As a result, Hauser-Feshbach transmission coefficients are a sum over all transmission coefficients for the exit channel that populate the same total spin and parity of the compound nucleus. Both approaches are valid for reaction modeling, and a number of different reaction modeling codes exist which employ both sets of formalism. Notably, Weisskopf viewing calculations are significantly computationally easier to perform, but may struggle to distinguish between the population of isomeric and excited states in a nuclear exit channel, due to the lack of conservation of angular momentum in this modeling approach. The statistical properties of excited nuclear levels have been a matter of concern and study for over 50 years. One of the basic statistical properties of levels is their density. A high level density in the compound nucleus at the appropriate excitation energy allows one to make use of the statistical model approach discussed earlier for compound nuclear reactions, as in this approach, the cross-section calculated can be described by an average over resonances. This is often reflected in the level scheme of many nuclei. The levels of a nucleus can generally be divided into two energy regions, namely the low-energy discrete states and higher-energy continuum excitations. This division arises naturally from the different approaches employed for their analysis. A spectroscopic approach for the low-energy discrete levels, and the statistical model for the high-energy levels in the continuum. Low-lying discrete nuclear excitations are generally small in number, well-separated, and rather simple in structure. For these levels, the spectroscopic approach is the most suitable, leading to information concerning configurations, residual interactions, and mixing. Additionally, these states are almost completely excited by direct reaction processes. With increasing excitation energy, the spacing between levels becomes progressively reduced, and the nature of excitations becomes more complicated as collective effects begin to dominate. In this region, the average spacing and widths of these levels becomes far smaller than those expected from a single particle model. As we move to higher excitation energies, the number of levels per unit energy becomes so large that individual states begin to overlap. This is independent of any sort of experimental resolution, but rather on the fact that the average level spacing begins to become comparable with the widths of the individual levels, which are in turn inversely proportional to the level lifetimes. As a result, it is necessary to use a continuous description, referred to as the nuclear level density, which represents the number of levels per unit of excitation energy. This nuclear level density is fundamental in nuclear physics, and is a crucial ingredient in all nuclear reaction modeling theory. It is within these quasi-continuum and continuum regimes that we can use the large number of nuclear levels to calculate cross-sections as an average over resonances, using the formalism of the statistical model as described previously. However, as the compound nuclear cross-sections predicted from the statistical model refer to population of individual states within a compound reaction mechanism, when we instead care about a residual production cross-section, we must instead use an effective or average transmission coefficient, representing the population of multiple compound nuclear states in the continuum, which contribute to the production of our final radionuclide. This can be done using the individual single-channel transmission coefficients from the optical model, as well as a nuclear level density model, which is often parametrized in terms of both the excitation energy and the spin parity of the compound nuclear state being populated. A number of different models for the nuclear level density are available in the literature and implemented in modern modeling codes. These include both phenomenological or semi-empirical models, which are global models fitted to experimental observables. Additionally, a number of microscopic models have become more recently available, which add in collective enhancements, such as shell effects, rotational enhancements, pairing corrections, and parity distributions, among other things, on a nuclide-by-nuclide basis. The selection of not only a good level density model, but a good parameterization of the model is vital for modeling in isotope production activities. Since the nuclear level density is used in calculating an effective transmission coefficient for the production of individual channels, the opening of individual reaction channels, including both their energetic threshold and how sharply they rise from threshold to their compound peak, are strongly dependent upon the level density model employed in an individual calculation. Since a number of residual product channels are accessible at a given incident particle energy, issues with the characterization of the nuclear level density affect not only the opening and closing of a single channel, but the transition and competition between it and neighboring channels as well. Another important ingredient in reaction modeling for isotope production is a well-characterized understanding of the gamma-ray transmission coefficients. These are typically calculated from one of a number of energy-dependent gamma-ray strength functions, and represent the competition between particle emission and gamma emission in highly excited nuclear states. Effectively, these models represent the color of the excited nucleus. A number of different models for the gamma-ray strength function exist and are currently implemented in most modern modeling codes. Using the gamma-ray strength function, gamma-ray transmission coefficients may be calculated, which enter the statistical model for the calculation of the competition of photon emission with other particle emissions. Gamma-ray transmission coefficients are important for the description of the gamma emission channel in nuclear reactions. This is an almost universal channel, since gamma rays, in general, may accompany emission of any other emitted particle. Like the particle transmission coefficients that emerge from the optical model, gamma-ray transmission coefficients enter the statistical models for the calculation of the competition of photons with other particles. One other vitally important aspect of reaction modeling is that of pre-equilibrium particle emission. These pre-equilibrium reactions are often modeled quantum mechanically as a multi-step process using an exciton model. In the exciton model, the incident particle can be imagined as, step by step, creating more and more complex states of the compound system, and gradually losing its memory of the initial energy and direction. This multi-step process proceeds through the creation and annihilation of two-component particle-hole pairs for both protons and neutrons, with each step characterized by transition rates, often expressed in terms of an effective squared matrix element for the average residual interaction. This process essentially acts as an equilibration of increasingly complex nuclear states, competing in each interaction with the emission of nucleons and photons. As a result, proper description of the pre-equilibrium tail in a reaction channel is dependent upon not only a well-characterized nuclear level density, but also knowledge of the exciton strength in the transition region to the compound nucleus model. This topic is of particular interest at the moment, as pre-equilibrium neutron emission tends to be severely underestimated in many systems. Now that we have introduced some of the core concepts and models used in reaction modeling, let us turn our attention back to the problem of parameter adjustment for modeling codes. Rather than blindly adjusting individual parameters based on cross-section data for a single channel, it is possible to instead develop a standardized framework to specifically go about improving predictive power for high excitation energy reactions. This process is akin to developing an early evaluation algorithm for energetic reactions for isotope production. So, how might such a framework actually exist? Our goal is to provide a logical process for adjusting parameters within a predictive code in a physically justified manner, accounting for both compound and pre-equilibrium effects, to ultimately find the best fit for high-energy reactions, similar to the evaluation of NX datasets for the INDEF database. Once a large number of strongly populated reaction channels have been measured experimentally, such a fitting process can begin. An example is presented here for the modeling of spherical nuclei. One first step is to select a base level density model to be used with particle transmission coefficients from the optical model. With a base level density model selected, a sensitivity study of the exciton model parameters may be performed to optimize the pre-equilibrium contribution of the reaction channel, as these parameters are key for the modeling of pre-equilibrium emission. At this point, local level density adjustments and optical model adjustments may be performed to optimize the individual single-channel transmission coefficients. This process repeats iteratively, adjusting level density, exciton model, and optical model parameters until an acceptable global solution has been found that matches the strongest independent channels observed in a set of experimental measurements. At this point, these improved cross-section calculations may be validated by calculating cumulative reaction cross-sections down a mass chain. As a result, such an example framework does provide a way to globally optimize all observed reaction channels rather than a single or small number of strongly fed channels. Turning our attention back to the cases of niobium-90 and molybdenum-90 production seen before, marked improvement in the compound region, as well as some slight improvement, is observed here in the pre-equilibrium regime. While much of the discussion of predictive codes for isotope production has until now been focused on the calculation of individual reaction cross-sections and excitation functions, this is not the only area where improvements in these codes are required. For large-scale production, there is a strong coupling of excitation function in nuclear data to a larger multiphysics context. Materials consideration, thermal hydraulics, and other aspects of target design are vitally important for the design of production targets, but are not the primary focus of nuclear predictive codes. However, one other missing puzzle piece connecting these two regions is that of particle transport, which is vitally important in conjunction with an excitation function for calculating the actual physical yield of isotope produced from an excitation function based on the energy bin subtended by the target, as this requires a well-characterized understanding of stopping power and particle transport in the target. Presently, computational modeling of neutron transport is at a satisfactory level thanks to decades of experience. However, one outstanding issue, which has become increasingly apparent in recent years, is a fundamental issue with charged particle stopping powers. In many charged particle experiments, corrections on the order of 5% for charged particle stopping powers are often needed to achieve consistency between experimentally observed yields and those predicted based on stopping power models, including both simplistic treatments such as Anderson and Ziegler, as well as more complex transport models used in multiphysics codes, including MCNP and Fluka. In recent years, it has become increasingly clear that these issues are largely not due to issues with the reaction data employed in these models, but rather with an underestimation of the stopping power of highly energetic charged particle beams. This problem is particularly dangerous, as it can lead to a number of different compensating errors in activation measurements, as well as redirect away efforts from isotope production activities which are of higher priority. A better characterization of charged particle stopping powers at high energies, as well as experimental benchmarking of these models, is a high priority for the isotope production community, as well as one with cross-cutting applications to other user groups as well. So, with this whirlwind concluded, we've now reached the end of this training module for WANDA 2021. While everything here has been presented at a fairly high level to provide more of an overview of both isotope production and some of the modeling codes currently used in isotope production efforts, we hope that it has provided some context for this session, as well as hopefully driven some interest for isotope production activities. We thank you for your attention and hope that this has been useful and informative, and we look forward to seeing you at WANDA 2021 as well as future years of WANDA. If you have any questions, please feel free to reach out to any of the session co-chairs, as we would love to hear from you. Thank you, and thank you again for your attention.